Science in pajamas. Yeah. All right. So today we're going to talk about Hooke's law for a spring. So according to Hooke's law for a spring, we have an equation. This is Hooke's law. And that is force equals the spring constant times the displacement or the change in the length of the spring. So as you know, springs, they can kind of stretch. I'm trying to see if I have one easily accessible, but I don't think I do. I'm sorry, guys. It looks like I don't have a spring. Oh, wait. Yes, I do. Yes, I do. I do have a spring. All right, so we have a little slinky, but it is a spring. So the x is the change in length. So if it starts from here to here, what is the change in the spring's length? And that's what x is referring to. Now, k is the spring constant, and a lot of that is based on the tightness of the coils and the material that the spring is made out of. And then the force is, what is the force needed to change that length? All right, so we have a couple examples of this that we're going to look at. Here's my first one. All right, so we have a spring with a constant of 0.80 newtons per meter is stretched 1.8 meters. What is the force? All right. So let's go ahead and look at this. So what do we know? We know the spring constant and we know how far it was stretched. So F equals Kx. We can go ahead and just plug right on in. 0.80 Newton meters times 1.8 meters. So the force of that would be 1.4 newtons. All right. Well, what if this same spring is stretched 6 meters instead? What is the force now? So we're going to use the same equation. And it's the same spring, so it's going to have the same spring constant. So 0.80 Newton meters. And the distance has changed. So this time we're stretching it much farther, 6 meters. When we do that, it changes to, the force becomes 4.8 newtons. Which kind of makes sense. Like even right now, I don't need a whole lot of force to stretch it this far. But if I want to keep stretching it beyond what it's normally doing, it's going to take more force to stretch. So I can easily take this whole spring and stretch it arm's length. But what if I need to stretch it farther than that? Now I have to use more force in order to stretch it even more. So it kind of makes sense. All right, let's do another one. See, that problem's all done. It's not that bad. You guys can handle this. You're smart cookies. All right, let's see. Here's my next problem for us. I just erase the board. There's my rag. All right. All right, so let's do our next problem, which says, how far, you guys can't really see that. There we go. How far will 25 newtons of force stretch a spring with a constant of 135 Newton meters, or newtons per meter, sorry. All right, so once again, we know our equation. It is force equals spring constant times the difference in the change in the length. Well, this time I want to know how far we're going to stretch it. I know my force. So force equals 25 newtons. I know the spring constant, 135 newtons per meter. I'm trying to figure out what the change in length is going to be. So that means I have to rearrange this a bit. So F equals kx, but I want to get x by itself. So I'm going to divide both sides by k. Cancels it out on this side and brings it over to that side. Left with x equals F over k. The force is 25 and the spring constant is 135. So we go through and we divide that, we could only stretch it 0.19 meters. So that means it's going to be a pretty sturdy string, or spring, not string. Not horrible? No, not horrible at all. Let's do one more. Alrighty. So we have a spring is stretched 1.2 meters by using a force of 32 newtons. What is the spring constant? So this time we know how far it's being stretched, 1.2 meters. We know the force needed to stretch it that. It's 32 newtons. What we want to find out is the spring constant. So we're trying to solve for K. That means once again we have to rearrange it. This time we want to get K by itself. So we're going to divide both sides by X. Cancels it out on that side, brings it to this side. So K equals F over X. The spring constant equals force divided by the change in length. So we have 32 newtons divided by 1.2 meters, and we end up with a spring constant of 26.7 newtons per meter. That is the spring constant for this particular spring. See, not horrible. You guys got this. I believe in you. All right, so that's what we're going to do for now. I hope this helped you to understand how to rearrange and solve these equations. And, guys, just stay safe and healthy. If you have questions, let me know. But, yeah. All right. Talk to you later.